Applications of the scalar product. Vectors and the scalar product are used extensively in physics, engineering, and architecture. As an example, in physics, the work done by a force is force times displacement in the direction of the force, or W is equal to F dot S. The units for work done is the joule. Calculate the work done by a vertical force of 10 newtons that moves 3 meters upwards. So here we have a vertical force of 10 newtons, and it produces a displacement of 3 meters upwards. So these are in the same direction, and therefore the angle between these two vectors is 0. So the work done is equal to the force dot the displacement. So that's the magnitude of the force times the magnitude of the displacement times the angle between them. So that's 10 times 3 times the cosine of 0, because they're in the same direction. Cosine of 0 is 1, so this is 30 joules. Find the work done against gravity by a particle of weight 30 newtons that decelerates for 25 meters up a slope of 15 degrees to the horizontal. Let's just draw that. So there's our slope and there's the horizontal. And we know that this is 15 degrees. And here's the particle sitting on the slope. And its weight, of course, will act directly downwards. It's decelerating as it comes up the slope here. So the angle between the direction of movement and the weight is 75. So work done is going to be F dot S. In this case, the force is the weight. So that's going to be the modulus of F times the modulus of the displacement times the angle between the vectors. The weight is 30. The displacement is 25 meters. And the angle between them is 75 degrees. Calculating, that gives us approximately 194 joules. Interestingly, for those people who do physics, if you work out the gain in potential energy from here to here, using the formula mgh, you get exactly the same value. So the work done against gravity increases the potential energy. Show that the diagonals of a square intersect at right angles using the dot product. So here we have a different type of application. We're doing a vector proof. So let's start with a square, and I'm going to call it O, A, B, C. And I'm going to define a vector A which goes from O to A, and a vector C which goes from O to C. Now we're interested in the diagonals. We want to show that they meet at 90 degrees. Note that this is a square, Therefore, the size of the vector A, the magnitude of A, is the same as the magnitude of C. Now, how do we get from O to B? We can go along C and then along A, so A plus C is OB. The other diagonal is AC. Backwards along A, forwards along C, so that's C take away A. Now let's do OB dot AC. So that's A plus C dot C minus A. And we can just expand the brackets. So that's A dot C plus C dot C. Take away A dot A. Take away A dot C. This cancels with this. C dot C is C squared. A dot A is A squared. And that's equal to 0 because of the point we made here. So we've dotted the two diagonals and we've got 0, and that shows that they are perpendicular. We're now in a position to do exercise 4.07 on page 138.